Everybody, please join me in welcoming Daniel Borkmann.
Welcome to my talk about BPF as a fundamentally better data plane. I'm Daniel Borkmann. I work at Isovalent, and together with Alexis Starovoitov, I maintain the BPF subsystem in the Linux kernel. So let's start off with what is BPF. BPF is really a general purpose execution engine. It has a minimal instruction set, and it was designed with two major goals. One, the mapping of BPF instructions to native instructions really has to have a low overhead, in particular on x86 and ARM64, so that the code can be executed as fast as possible. And two, the BPF instructions, they must be verifiable for safety, so they cannot crash the kernel or destabilize it otherwise at the time when you load the program. And the kernel itself, it provides the framework and all the building blocks. For example, the BPF helpers, where the BPF program can call out into the kernel, or also the attachment points where BPF program can be executed from when events are happening. And so that question is BPF a generic virtual machine? No, it's not, because it's also not the design goal. You have KVM or other things for that. Is BPF a fully generic instruction set? It's not either. So BPF is an instruction set with the C calling convention in mind. What does it mean? The kernel is written in C, and BPF basically has to efficiently interact with the kernel. There are approximately 150 helpers for BPF that can call kernel code, and around 30 different map implementations, which is a shared storage, key value like storage between BPF programs and also from user space. BPF is really minimal. So it has around 114 instructions and 11 registers, of which 10 are general purpose. And if you compare it to x86, it has over 2,000 instructions. So it's really just very reduced. And LVM has a BPF backend that is able to translate so-called BPF restricted C into BPF instructions. So how far off is this restricted C from generic one? The BPF verifier has seen major advances in the past year or two. So with that, we are able to have real function calls in BPF. There are bounded loops, which means programs cannot loop forever, but there has to be an upper bound, which can then be enforced by the verifier. There are global variables. There's static linking. We have something that's called BTF, BPF type format, which is a data format where you can describe, for example, structures or functions, and that's heavily used. And there are over 1 million BPF instructions that you can execute per program. And that really allows for solving a lot of interesting production use cases already. I picked a few interesting ones that may not be that obvious. For example, one of them would be to reduce the kernel's attack surface with BPF. For example, if you have a packet of dev type scenario where it can really kill the machine, those things, they don't happen frequently, luckily, but we had an occurrence in the past, and I want to dive a bit into that. For example, like in this case, it was about calculating packet hashes. They are used in a lot of places in the networking stack. For example, in the receive path, for steering traffic between CPUs. And in case a packet hash from the network card does not have enough information, for example, only covering L3 headers, but not L4 headers, then the kernel would recalculate this hash in software in order to be of higher quality. And that is done by the so-called kernel flow dissector. It will basically parse the packet and use all of the information it can get. It will even go into encapsulation and then derive a hash from that. And in this case, that packet of dev was, if there was an IP header with an invalid header length, then it would basically loop forever. And that bug was basically exposed for 2 years, and it hit production kernels. So a traditional workflow would basically look like this. You wait and like the patch gets sent to the mailing list, you wait until it hits stable kernels, then distributions backport it into their own kernels, then you have to test it in your environment, making sure that the kernel upgrade doesn't break other things, and then you have to successfully roll it out into production, which also means you have to steer away live traffic for those nodes that you successfully reboot. But in even like traditional tools like NetFilter, they could not have protected you in the meantime, since that packet hash can be calculated much earlier point in the receive path than as if it would hit the NetFilter subsystem. And that is quite bad, because it really means that all your machines are exposed and they could potentially be killed by an attacker. So BPF-based workflow would have two options to improve that situation. One is you could drop those bogus packets right at the XDP layer with BPF. And that means you can attach a BPF program atomically while live traffic is flowing. And that, of course, means you don't have to wait for the distribution kernel in the meantime. You don't have to reboot, or your services are not getting disrupted. And you can plan a kernel upgrade at a later point in time without extreme pressure. The other option would be like to replace the kernel's flow dissector with a flow dissector written in BPF. And that is possible today. BPF programs, they're here used for the packet parsing, and they can be tailored to the production use case that you have, which that also means that it doesn't have to have all the code for all the different protocols, but you can only restrict it to what you really use in production. And that also means, because it's BPF and it goes to the verifier and the safety check there, you don't have any out-of-bound access to the packet, for example, or you don't have looping forever. Otherwise, it would be rejected. And that can also be rolled out atomically without service disruption. So that's one area. Then another one is improving the kernel scalability and extensibility with BPF. Let's take a look at the cloud native example. Oftentimes, service load balancers are co-located with regular user workloads in every node. That's, for example, the case with Kubernetes. And you can really gain a lot and reduce CPU costs significantly if you move the load balancing from legacy subsystems, for example, NetFilter over to BPF at the XDP layer. And you can even achieve DPDK-like speeds with it. Some time ago, we did an experiment and compared XDP with DPDK in terms of raw forwarding performance. And you can see like XDP, when you push the packet out to the same interface that it derived on, it even gets better performance than DPDK. So you can see like the XDP reaching up to 70 million packets per second for 4 cores, and DPDK in comparison only 40. If you send out a different NIC, then XDP is slightly worse than DPDK. But for the same NIC scenario is perfect, for example, for use cases like load balancer on the stick. And similar can be done for moving the firewalling policies from the kernel stack down to the XDP layer. And you can then free up CPU cycles that you can otherwise spend on user workloads. For example, the DDoS packet drop performance comparison. You can see DPDK is still performing slightly better, but XDP has a significant better performance compared to the regular kernel stack, which you can see in those 2 graphs below here. And looking at the CPU utilization, DPDK is busy pulling the NIC, and if you compare that to the kernel stack, it basically goes into almost 100% software interrupt processing for the regular stack here in purple. And with XDP, you can see from the orange line, you can get a much better utilization because you don't have to do all the work until you drop a packet. And that all happens with the upstream kernel drivers that have XDP support. You don't have to busy pull CPUs, and there's also no user kernel boundary crossing. You can, like, given that BPF, you can reuse existing kernel infrastructure. For example, like you have those BPF helper functions that can do routing lookups, just to mention one. such BPF XTP load balancers are implemented, for example, in a couple of projects, Catran from Facebook, Solium from our side, and also Unimog was recently announced from Cloudflare. I've put a couple of links below here for reference. And BPF, the BPF, if you have a BPF data plane, that also helps for policy enforcement or moving traffic from and to containers apart. So it's not just the north-south load balancing path, but also for the containers, it will improve. One example here is where you can attach BPF programs to sockets so that they get executed on connect, send message, receive message, and so on, system calls. And what you can do with that is, for example, implement load balancing or policy. The BPF program can then reject, for example, and throw an error to an application even before crafting a network packet. And it can also rewrite the actual addresses, like the service address and port that, for example, like a TCP connect call issued, and you can already rewrite it to a backend right there. And that happens before a packet got generated, so you won't have a packet-based NAT in that case. So the kernel keeps on using that backend address for the remaining lifetime of the TCP connection, which is really great. And those BPF programs, they're attached to cgroup v2 in this case, and this really allows for fine-grained policy and also scalable, because you don't have all the rules in a global in a global scope in that sense, but they're just scope per pod, and you only execute that for this particular pod, but not for the rest. And another area is the traffic path into the pods. In this example here, this is the typical example where the traffic arrives on the NIC and then it gets pushed up the host stack for the routing, packet filtering, etc. And with BPF, there are on the most recent kernel 2 new helpers. One is called redirect peer and the other one redirect nay. And that basically allows for only doing the forwarding in the so-called TC BPF layer, where you can then push it right into the pod. And that redirect peer helper, it allows for a low latency network namespace switch from the NIC into the pod for that traffic. And the other one for the reverse direction, and it will automatically do the layer 2 resolution and populate the layer 2 addresses on the network packet. And this then allows to avoid the host stack. The firewalling policies you can implement in BPF anyway. And with that, the performance can be significantly improved. For example, in the first bar, you see a TCP send file number for the node-to-node case, basically our baseline here. And then a pod to remote pod case where you have the routing via stack. It only gets about half the performance. But if you use those 2 helpers in combination that were recently added, you will get the native performance again. Same for the TCP request response performance tests. Numbers here are similar, like the pod to remote pod case where you have the routing via stack is even worse in terms of transactions per second that you can achieve. Another case that is quite interesting is what BPF can help with is to implement lockless rate limiting, in particular on multi-queue devices with a concept that's called earliest departure time. In that case, the BPF program classifies the network traffic to pods or specific applications, I mean, however you want to classify it, and then it sets a packet departure time based on a bandwidth rate that the user defined. And lower in the TCP QDisk layer, you have so-called fair queue QDisk, which can then schedule this packet under this timing constraint, which means the BPF program sets the timestamp and FQ ensures that the packet is not sent earlier than that. This is basically how it looks like. You have the BPF program, it does the classification and the setting of the timestamp, it goes to the multi-queue, and then you have FQ leave QDisks, and then it gets sent to the wire. And with that, if you compare that to the traditional approach, which would be the hierarchical token bucket, which cannot be implemented lockless on multi-queue devices, you can see if you switch here to the BPF and FQ QDisk combination, then for the 99th percentile, you get a 10x latency transmission reduction, and 5 percentile, you get up to 20x latency reduction, which is really cool. There are also other examples, for example, TCP congestion control algorithm that you can implement with BPF, or custom TCP header options, which is really interesting for, in particular, for data centers. Here I posted an example where on the left side you see the implementation from BPF, and on the right side you see the actual TCP cubic implementation as native code in the kernel, and they are very close to similar. And that allows like a short turnaround time for experimentation, to develop your code and to deploy those changes. And given their safety check by the verifier, it's another great property. And also you have a stable API in contrast to kernel modules, so you don't have to deal with messy upgrades. And even for the congestion control case, it allows to interoperate and extend that feedback with data you gather from other BPF programs. For example, think of BPF tracing programs that could influence those decisions, or programs from the TCP header options, for example. And yeah, that really overall also simplifies the control plane when BPF is used in multiple subsystems, because you only have to orchestrate BPF itself. There are less dependencies and other moving parts. So it really feels like, so extended BPF has been around for 6 years, and it really feels that potential is so huge that we're still at the very beginning. How could the future look like? I mean, we see more and more functionality that is moved into BPF, and in the end, we may end up with really just a tiny core kernel with a minimal attack surface, and the rest around it could be enriched through the BPF subsystem. So yeah, with that, I would like to thank you, and opening up for questions.
Thank you very much, Daniel. What a fantastic presentation. It sounds like you're working on this on a daily basis. Getting back to the Q&A for Daniel's talk, I have a first question. First of all, let's give Daniel a round of applause. I completely forgot that for the fantastic presentation. And then for my question, at what point did you realize that eBPF will change the Linux kernel forever? I mean, you have been involved with eBPF from day one. There must have been a moment where you realized this is going to change the Linux kernel for good.
Yeah, it's a great question. I think at the moment when the BPF patch said that the very first one got merged, I still remember I was at the airport waiting for a plane to board. And then I saw the message from David Miller that he applied the patch. And for me personally, that I realized that that has such huge potential. But of course, I didn't think back then that it could change the whole world like it does today. So, but back then when networking and tracing really got their capabilities as they have now, that really changed it. And overall, like the community and the use cases and the issues they are solving with eBPF, that took it to a whole nother level.
Excellent. Yeah, I think I think my thinking around that is actually very, very similar. We have another question from Tristan. You mainly discussed networks in XDP, but what is the potential for change with regards to trace points, K probes, and U probes?
I think some of the other speakers, they will cover this in more detail. But basically, you have an ability to introspect all the different data structures in the kernel and combine even the data that you collected from multiple trace points into an information feed that you then export to user space. You can customize all of this, and this was not possible before. So it takes the whole tracing observability to a new dimension. It's probably just a short answer here, but there are many more details from the other talks. So I would recommend to go and watch that, given we just have a few minutes.
Gavin is asking, can I play around with XDP in KVM?
You can. So there, of course, you always have to make sure that the underlying driver supports XDP, in particular native XDP itself. Word.io.net driver does that. But there's also generic XDP. Generic XDP, I would mostly recommend for experimenting, but not necessarily yet for using in production. But a driver that has native XDP, you can definitely, I would definitely recommend.
And then Nick is asking, different Nick question mark, XDP can send back a packet to another Nick than it received it on.
Yes, it can. So BPF programs and the XDP, they have different return codes. One of them is where you can send the packet back out the same NIC, but there's also another return code, which is called XDP redirect, where you can send it a different NIC. So that's definitely possible. Both NICs have to support XDP natively, however.
And then final question from Qingrong Chen, can we have multiple eBPF programs using XDP on the same host?
Yes, you can. That functionality was recently extended to the XDP, and you can, since quite more or less recent kernels, I would say like 5.8 or so. I would have to look it up again and give you the answer in Slack.
Excellent. I think we're running out of time for Q&A for this session. Daniel will stick around on the Slack channel and we'll be able to answer more questions. Let's give Daniel another round of applause.